Okay, so hello everybody. Thank you for invitation. It's very nice to have such kind of live event in our hard times. And today I will talk about big data, a little bit about big data, and mostly about astroparticle physics. So recently we established an astroparticle physics lab at JetBrains Research, and I will just try to give you some kind of impression what is astroparticle physics is, what are the challenges in terms of big data or computing, and how we actually try to cooperate within these conditions. Yeah, so here's a kind of short outline of my lecture. So first of all, I just want to emphasize that astronomy or astrophysics or astroparticle physics, they are observational science. So actually we cannot kind of design, experiment, or tune our setups, like for example, Large Hadron Collider. And moreover, sometimes we have a transient events which are not kind of, constant shining of the stars or whatever. And they're of a special importance because they can appear like once per year or per decade or per 100 or sometimes even per 1,000 years. Yeah, and so just I assume that not all of you know what is astroparticle physics is, and I first start from astronomy. So actually astronomy is kind of electromagnetic astronomy. Then I go to particle physics, and then I actually try to explain what is astroparticle physics is, and then we go to multimessenger astronomy, and in the very, very end only I will give a kind of impression of data science project in astroparticle physics, and as well give some examples of what we are doing here in the frame of JetBrains research. So first is electromagnetic astronomy, to give you an impression. So why we say electromagnetic? So you know that the photons or gamma quanta, they have a different wavelengths and a different frequencies, and in principle we can make an image or make a plot of every astronomical object using a different wavelengths. Yeah, like here you can see the very famous Crab Nebula. Yeah, what was actually exploded. Yeah, about, as far as I remember, about 1,000 years ago. And so it's actually some nebula around this and the pulsar in the very center. And in principle, as you can see here, we can actually scan the different structures of this nebula, yeah, from very low energies, from radio to the very high, to X-ray, yeah, and in X-ray you can already see the signatures of the accelerated matter, so it's like a kind of a whirlpool, yeah, which kind of gives such an emission, yeah, and in this plot you can see the physical mechanism. So actually, yeah, we try to figure out what happens there just only by scanning some of astronomical objects in different wavelengths. Yeah. So actually here below you can see the parameters of it. So actually, I mean from this time. So SN 1054. It's actually when this event happened. So it's already expanded in 11 light years, yeah, in 1,000 years. So this matter are very fast, and so actually we even with the Hubble, maybe you see this famous animations, and we actually see how the matter is expanding. So yeah, so I told that we scan astronomical object in different wavelengths, yeah, and here in this very nice plot. So actually you can read more in this, so you can see, yeah, so what is the kind of temperature, yeah, so the gas, it's so-called cold gas, yeah, it's 600 Kelvin, so it's not very cold, like not very it's cold in terms of space, yeah, but it's like 600 K, it's pretty hot here on Earth, yeah, but when this gas collides, it produces radio waves, yeah, so cold gas. And so when we actually start to go actually deeper in atomic structure, yeah, for example, when we start to excite electrons in electronic shell of atom, or when we start to make a plasma, we can actually produce a different gamma emission in different wavelengths. So actually you can see the scale of it, yeah, like, so this one is a visible light, and we can go to X-ray, to gamma ray, and actually to very high energy gamma rays. So, I mean, this will not be visible in, yeah, in stream, but so if we actually, yeah, start to expand this, I guess it will go to the next wall, or maybe like a few hundred meters from here. So it's actually the range we can scan. And so this is, so maybe you heard about this partial wave duality of photons. So, and actually when we go to the very high energy, so each photon is already like a really particle, and we can detect this particle, a single one. Yeah, and so here you can see a kind of zoo or different set of experiments, and yeah, thanks to our atmosphere, very high energy emission is kind of, yeah, shielded, and so we need to actually run a different satellites to measure this emission, yeah, because atmosphere is not transparent. But again, when we go to the very high energies, so these particles can already collide with atmosphere and make huge cascades in this. So what is actually kind of how we transport from astronomy to astroparticle. Yeah, and I would like to show this very nice plot. So this is, yeah, this is what we actually was discussing like during last 5 minutes. So we have electromagnetic astronomy, and you can see on x-axis the wavelengths, yeah, so sorry, frequency, so 1 gigahertz to 1 TeV. So this on y-axis you can see the time. So actually it's 0 years, this is 400 years ago. So I guess it's just arbitrary attached to the discovery of the telescope, yeah. So optical astronomy is pretty old. But when we speak about radio or high energy gamma ray astronomy, so we can see it's started to develop only like last 50 years. And as well, so this, we also cover this very high energy astronomy, and as well we have cosmic rays and the gravitational waves here. So in principle, we have a lot of different so-called messengers to study our universe, but yeah, most of the time we look on the very, very narrow range. So most of the emission of universe is actually uncovered, yeah, by humanity, and we only started to do like in last 10 years or 50 years to be more conservative. Okay, so now I come to my most maybe complicated part. So I just want to explain, yeah, why we come from astronomy to the particle physics. And I will just very quickly give you some overview of the particle physics. I guess you know the standard model from many popular lectures, book, and so on. So yeah, so our matter is actually consists of the elementary particles, and these are the zoo of elementary particles. Yeah, so for example, nuclei of hydrogen is not elementary particles, yeah, because it consists of protons and only of one proton if you speak about hydrogen. Yeah, but actually proton is also not an elementary particle, it consists of quarks. And actually, yeah, all of these particles are connected with so-called bosons. For example, yeah, strong interaction fields are connected with, is transferred with gluons. So photon, you know, it's like electromagnetic. It connects almost to every particle except neutrinos, and so on. Yeah. So here you can see very famous Feynman diagram here, how this particle interacts. So yeah. So this, for example, yeah, very complicated one. This gluon interaction, and more simple electromagnetic one. Yeah. So just how we can connect different electrons and positrons. Yeah. And so actually everybody of us knows that we can, yeah, simulate this interaction in our colliders. So we just collide very high energy particles and try to study these forces, but we are really limited in energy. So our limit is TeV, so 10 to 12 electron volts, but with astrophysics we can go further and further in energy, but still studying the same processes like here, but in the very extremal range. Yeah, and so here I just want to show you things which are not very, common used in our life. Yeah, so you know that the matter is consists of baryons like neutrons and protons, but actually baryons can be of a different type. So I will show you. As well, there are mesons. So these particles can be produced only during high energy collisions because they are unstable. And there are others very exotic particles which also can be produced, but they are very short life, like 10 to minus 20 seconds and so on. So they decay just immediately. And as well, there are like pentaquarks, yeah. So it's like baryons with the 5 quarks and so on. So it's like actually zoo, which we can only study in laboratory. So they are not very common in our life or in atmosphere. But I will speak about this later. Yeah, and here's a kind of zoo of baryons. So we know only these two guys, but in principle we can produce whatever we like. So thanks to the mathematics, there's like Lie theory with a group theory, and this group theory is actually very nicely predicts these particles. And in principle, we can calculate their properties and produce them at our collider. So this particle physics are very nicely described, and as well as mesons. Yeah, it's also very symmetric. So our nature is actually on this level at least very compact and symmetric, and we can simply explain what is going on. Yeah, and okay, so I was speaking about particle physics and so on, and you asked me, okay, how this actually connects to astronomy. But yeah, if you remember, on Earth we have gold, mercury, and so on. And actually these guys, if you can look here, so they actually produced in a very energetic processes like supernova explosion or merger of neutron stars. So actually, again, we go from the very basic particle physics to very energetic phenomena in space, in universe, and then we just actually can connect. So this is, I guess, it's a very beautiful picture how we go from the very microscopic level to the macroscopic one. Okay, so hopefully not very bothered by this very mathematical and basic things. And now we just go to very experimental particle physics. It's very funny and at some point a bit more simple as my point of view because I'm astrophysicist. Yeah. So okay, so cosmic rays. What is a cosmic ray? So kosmische Strahlung in Germany. So more than 100 years ago, it was already discovered with a very simple instrument that we have a radiation, coming just from everywhere. Yeah, it's a kind of natural radiation. And there was a hypothesis, that this radiation should actually decrease when we increase the altitude. So if, for example, we just jump into balloon and start to measure the count rates of this radiation with an altitude, this should actually fall down. In principle, this is valid for very small altitudes, but if you go higher and higher, the count rays become larger. What does it mean? It means that radiation comes not only from below, but also from above. And this is what was actually discovery of cosmic rays. So at that point, people, scientists, had no idea. So what is the composition of this cosmic ray? So it was like a race, So here from Strahlung, because it discovered by have to. It's F5 maybe, or Control F5. How to make this full screen? Mm-hmm. Okay, so what I was speaking about. Okay, so at that point we don't know about the composition of this cosmic ray or kosmische Strahlung. And people start to investigate this, and actually it turned out that in principle it's not only like a single particle or single counts, in the very high of atmosphere. But if we actually make a kind of array of synchronized detectors, so we can see some kind of showers. So we see that these counter arrays are start to count at the same time. So it was discovered in parallel by Perroget in France, and later after Second War by Dmitriy Kostunin in Soviet Union. So it was like, let's say, starting of, I would say, high energy astroparticle physics, because we detect not only single particle but very high energetic particles by measuring the cascade of a secondary ones. Okay, and so this actually what they measure. So we have initial particle, for example, proton, which collides with the nuclei of atmosphere, and yeah, due to physics, so it actually loses like about half of energy after each collision. And yeah, you can imagine if you have energy of, let's say, 10 to 20 electron volts, so it's like a measure of energy. It's like a billion times higher than at Large Hadron Collider. So you can imagine how many particles you can produce. We can calculate them, we can simulate them. Yeah, for example, here on the y-axis, you can see the number of particles. Yeah, so most of them are just gamma and electrons and positrons. Yeah, so you can see this 10 to 10. Yeah, it's billions. And here is actually an altitude, yeah, of a shower development. So, for example, so what this plot says, yeah. So if you have, say, a very vertical particle collides with our atmosphere, so let's say the shower starts to develop at 10 kilometers, it reaches its maximum at 7. So it develops during the 7 kilometers. And so, yeah, the maximum of number of particles are just billions of years, billions of gamma quanta and millions of hadrons and so on. Yeah, so hadrons, these particles consist of quarks, just to remind you. Yeah, so it's very intensive phenomena, which you can see. Yeah, and this electron, exa-electron volts, and we can go to zeta electron volts, so it's like 3 orders of magnitude higher. Yeah, so how we actually can detect, yeah, these particles. So yeah, just to remind you that we have a different, yeah, so pi, it's actually mesons, so what I told is very unstable particles. So they just decays in different, yeah, subparticles, and we actually can detect kind of stable or long life particles on the very surface. So like muons, they're also unstable, but it's kind of long life. So the life, I guess, around microseconds, but due to, yeah, special relativity, so time is actually compressed during the propagation. Due to this, they can reach actually the surface. Yeah, and then we can simply put a different particle detector and detect particles like we do in colliders. Yeah, and as well, atmosphere is also excited and can produce fluorescent emission, and as well as so-called air Cherenkov emission or even radio, so we can detect different parts of this shower. As I told you, though, in astronomy, we can also scan our astronomical object with different instruments. Actually, the same way for air showers. So we actually scan this very complicated air showers with only one goal: to define what actually initially arrived to our atmosphere. So we actually study the secondary process very intensively to define just like 3 numbers, yeah, direction, energy, and type of the particle. Yeah, so here I just want to show you largest cosmic ray observatory in the world. So we just use that observatory, just like a few telescopes and so on, yeah. But to detect these air showers, so we just locate 1,000 of these tanks. So it's like a really tank. So it's kind of size of this stage, filled with very pure water with a very sensitive detectors to detect these secondary particles just passing through this tank. And as well, there are fluorescent telescope yet to scan the optical component of this air shower. And they are actually distanced against each other with a distance of 1.5 kilometers. Yeah. And the total area is 3,000 square kilometers. So it's actually what we have to build to detect this very single particle. Yeah. So in this very example, you can see, yeah. So if the distance is 1.5 kilometers, so this single particular air shower just covers of a size of 10 kilometers. Yeah. And if you go to highest energy, this will cover an area of 100 of kilometers. Yeah, this is located in Pampa Amarilla in Argentina, so it's a very nice plateau, very flat one when we can actually fill. Yeah, unfortunately, it's not fully filled because there is some firms which are not really kind of fans of the cosmic rays, and they say, no, please don't put your evil detectors there. So there's unfortunately some holes in the detector, but in principle, yeah, it's operate very nicely for 20 years already. Yeah, so cosmic ray spectrum. So actually what we measure is cosmic particles, yeah. In principle, you can see here two plots, one very detailed, one less detailed, and this guys actually measured in a space. So what we can do, we can just build a kind of detector very similar to collider one, yeah. So of course, not as big as like an LHC, which is like 30 meters, yeah, in diameter, but we can make a bit smaller, still tracking, so we can very nicely define the charge of the particle and its energy. Yeah, and here we can see that we can measure different spaces of particles from hydrogen to iron. So why from hydrogen to iron? Because these are most abundant particles in the universe, because due to different processes in the stars, so star can burn only to the iron. So actually stars has an iron core. And to produce more heavy particles, we just need to wait until it, let's say, explodes as a supernova, or for example, two neutron stars just merge, and this actually produces some kind of very energetic shock waves. And these shock waves, for example, heavy particle actually can acquire some neutrons and became more heavy. In principle, we reproduce the same, for example, in Brookhaven laboratory or in Dubna, when we try to kind of glue these very heavy elements. Yeah. But when we go to air shower, so you can imagine, we have single particle. This particle actually collides with atmosphere, produce huge cascades with a size of tens of kilometers, and this super ultra complicated to reconstruct what actually arrived initially. Yeah, I will show you later so how we can roughly distinguish, but so this is like just a common spectra of cosmic rays. So here you can see it's like a bit less experiments than here, because these are kind of space one or very sensitive ground ones, but this is just a pure ground ones, which actually started from about 50 years ago. They measured, you can see, from 10 to 13 to 10 to 21. Yeah, so it's like 8 orders of magnitude of cosmic rays. Yeah, so the universe is so diverse that it's produced a really huge spectrum of these different particles, and actually you can see some anatomic structure. So it's like a knee, second knee, ankle. So this knee, second knee, and ankle means that the spectra change its slope. When spectra changes slope, that means that we likely have suppression of the flux, or maybe we have to switch between different accelerators, because, for example, supernova cannot accelerate particles infinitely, and some particles actually is kind of enclosed in the galaxy, so they cannot actually escape them, and so on. And this actually structure, so it might be a bit chaotic, but actually if we study this and try to define a model, so we can actually estimate the number of particles produced in our galaxy, extra galactic, so from direction which arriving from not like a kiloparsec scale, like a scale of our galaxy, but from megaparsec or even gigaparsec. Yeah, and around second knee and ankle, so this region is of a special interest, because it's kind of expected that we have particles arrive just from outside, not produced in our galaxy. Yeah, and we can extract very many features from this, but actually it's again one of the beauty of nature that we actually study like this. Three different numbers, like a flux, which is actually described. I mean, if of this small piece described as just a single power law and mass composition. from these few numbers, we just, let's say, imagine how the processes is going on in this cosmic accelerators. Yeah, so this is mass composition, so you can see, yeah, so the abundance of the different primary particles. So you can see there's some more abundant, some less, because of the processes actually happening in stars. Yeah, sometimes, for example, yeah, we can yeah, more simply produce, for example, silicon, yeah, than chlorine, so on, just because of this nuclear process. We will not go into very details. Yeah, and so we can arbitrarily divide these types by logarithm of the mass. Yeah, so the mass of, for example, iron is 56, so it's 26 the charge, so it's like equal to 26 electrons, and the rest is the neutrons, and as well, so proton or hydrogen has a logarithm of A equals 0 because it has only single particle in nuclear, single proton. Yeah, and so here we can see how they how we can distribute these four groups in a more rough representation. Yeah, and when we go to very high energy, we can say, okay, this particle are light, this particle are heavy. And this is actually, yeah, we see how they, I mean, the solid line here is just an entire flux and the red points. So you can see the author of this work just arbitrarily crossed some points. They say, it's a very strange result. They can broke our feet. We just drop this point. So you can see that science is not as simple as one can expect. So it might be some really discrepant stuff. And so what's the most interesting is the very tail of the distribution, because so actually the nature of particles on this tail can tell us what we actually have in the surrounding universe. So if you have only heavy particles on the tail, so you can see that the uncertainties are very high. So it's really hard to distinguish, I mean, what is the composition of the tail, yeah? Because it's like just a few or maybe a bit more than 10 at lower energies, the number of particles, so very few. So we just need to wait a long of time to measure them. And if you have a light tail, that means that most likely we have kind of a horizon which we cannot see any accelerators, because with increasing of the energy of particles, more easily collides with the photon background of the universe. So you know that we have a photon background, I mean, which actually produced on a cosmological distances and so on. And this very high energy particle just collides with the photon and start to disintegrate. And when this particle actually passes a gigaparsec of distances, so it loses energy at each of this interaction. But if you have a heavy tail, that means that our acceleration is just exhausted, because particles with a higher charge, and this means more heavy, is easy to accelerate. So if you see the heavy tail, that's most likely there are no more possibilities in the universe to accelerate these particles. So I would say it's kind of very fundamental. Yeah, either we just cannot see behind the horizon, or we can't accelerate this more. It's question goes to, I guess, even maybe to philosophy or to cosmology. Yeah. So whether we don't see or we don't have, it's like very interesting one. Okay, but as I told you, yeah, so cosmic rays are charged, and we have a lot of magnetic fields in our galaxy, universe, and so on. And actually, we cannot trace the source of the cosmic rays. So here you can see the sky and cosmic rays. Yeah, it's very contrast, but actually fluxes from 0.38 to 0.46. So in principle, the sky and cosmic rays are almost isotropic. So this one is actually produced for the very high energies, and in very high energies. So it's a galactic coordinate. So here's the galactic center, and it's like a galactic plane. And in galactic coordinates, yeah, we see that okay, there is some strong indication that we have a kind of bright spot. I mean, really huge ones, like a 40 degrees. Yeah, so the size of the moon is 0.5 degrees, like a piece of sky in like 100 moon times 100 moons. So it's almost impossible to define the source. but at least it's kind of clearly visible that they are not arrived from the galactic planes. They are of extragalactic origin, starting from 4 exaelectron volts. So it's kind of indication of their extragalactic origin. Okay, and so my next point, it's very funny that we detect such high energetic particles, but we have no idea from where they come. Yeah, and so we need to search for cosmic ray accelerators. And I told you that cosmic rays are charged, and the charged particles are actually deflected in magnetic field. But how can we trace the source? Then we need some neutral particle, right? So if particle has no charge, then it's just propagate straight, and can point us to the accelerator. Okay. So which kind of neutral particle we have? The most obvious answer is a gamma. It's a photon. So we know how to work with photons. We can produce photons in laboratory and so on. And then we can go search for photons. The main problem is that photons are very suppressed in the flux. It's really hard to distinguish them from the cosmic rays. And actually to detect them with these surface detectors, with these tanks, are pretty tricky. And for this, as the first step, community start to build such a huge so-called air Cherenkov telescopes. So, I remind you about the Cherenkov effect. So there were 2 Soviet scientists, Vavilov and Cherenkov. Cherenkov was just a PhD student of academician Vavilov, and he just discovered that if you have a very fast particle which moves in the medium, so you know that the speed of light is actually lower in media than in vacuum. This is not valid for the massive particles. In principle, you can accelerate massive particles faster than light. I mean, faster than light in media, but not faster than light in iron. This is so-called also like a kind of break-in emission or Bremsstrahlung emission. So the media start to react and emit a light. And so you can see this Cherenkov light in reactors. So you can just Google photos of reactors. This blue light, in water, in very dense media. But this can happen as well in atmosphere when we have such very fast-moving particles. And so you remember that we have a lot of electrons, a billion of electrons, and these electrons can produce a Cherenkov light. And we can detect this. So it sounds very simple, but actually these electrons are not so many. And for this, we need to build telescopes with the mirrors of 10 meters. So these mirrors are not as make my mic. This one. So these mirrors are not as nicely tuned as for astronomical telescopes, but the main advantage is actually to collect as much light as possible. And so actually you can see the photo of this shower. So you just imagine that the showers has a kind of sizes of kilometers, and this have only a few pixels in our cameras. And actually this image consists only of about hundreds of photons. So we built like 10 meters mirror, reflect this, and we get only like 300 photons of each shower. So this is very, very fine phenomena. And to detect the single photon, we need to use so-called photo multipliers. So it's very sensitive detectors, and so if you accidentally turn them during daylight, so you just destroy your camera completely. So just blown, because it has a voltage of kilovolts or sometimes 10 kilovolts. And so this was a Whipple telescope, so the first successful one. So it's built in Arizona. Of course, there was some prototypes in Russia, England, and so on. But I mean, the first working one was this guy. And as I told, so the detectors are very, very sensitive. And the first camera, so here, so it was built in late 80s, and it had only 37 pixels. So you know how many pixels have your iPhone, And so the first successful Cherenkov telescope has only like less than 100, But I mean, now it's not much better. Now it's like a kilopixel, something like this, yeah, because one pixel costs like order of €1,000. So it's very fragile and so on. Yeah. So here, yeah, we can see. So this actually, the mechanical construction was very successful, and you see it was like a 6 upgrades of the camera, and this telescope still operating in Arizona. So it's actually how we can reuse a nice instrument many times. Okay, and I will tell you a little bit about Hess because I working on Hess. It's called High Energy Stereoscopic System, named after Victor Hess, who actually discovered cosmic rays. And this is actually the bird view of the array. So we have 4 telescopes with 12-meter mirrors. So this distance between them about 200 meters, and we have a really huge guy in the center. I don't know, maybe because yeah, people like to build the largest chunk of telescope in the world, and they build this. It's 28 meters of mirror, but the funniest thing is that since it has really a huge mirror, it's sensitive to the very weak phenomena, and it was built actually specially to study a transient. And this big guy actually moving much faster than the small ones. So it's a huge metal construction made on yeah, you know, uh, in a special dock when actually the huge ships built. I guess it's partly built somewhere like in Hamburg also, yeah, and then transported to Namibia to Africa. This guy very fast, so you can see. So it rotates, so can cover 90% of the sky in 1 minute. So it's megaton stuff. There's also other chunk of telescopes. For example, in La Palma, when we have this volcano eruption now, fortunately, this telescope stays on the another summit. It's not, at least now, not, let's say, really affected by this eruption, and they have carbon structure. So it's 2 different approaches, both actually successful. Yeah. And so since Hess is located in southern hemisphere, yeah, it's very suitable for studying galactic plan because most of the galaxies are visible from the south. And here, actually, yeah, we can see how the skies looks in a light of particles exceeding the energy of Large Hadron Colliders. So it's just a colliders in our universe. So you can even see some shell structures. So it's supernova, and we really see it's very bright in these particles, which we need to invest like $1 billion to accelerate on Earth. Yeah. So for example, here, yeah. So this one supernova 1006. So it's again was explosion like 1,000 years ago, roughly. Yeah, and you can see very nice, very kind of high resolution proton X-rays, and I guess red is some dust, maybe it's optical ones. Yeah, so we can see this blue X-ray shell here, and we can also point our Hess to the supernova and see how it looks like in gamma rays. So it's not very nice resolution. Yeah, we have really huge machine, but we can produce like this. So PSF is like kind of point spread function. So what does it mean? This means if we have a point source and we process this point source through our telescope, so we get this kind of smeared one. Yeah, but just to let you know, so actually, I mean, this image is constructed from the single photon, so we detect only single particle. It's not like a truly photon. So you can see, so this very bright one consists just 50 photons. So we make some special sampling technology to make this funny plots. So you can see it's like only like a few thousand of events in this image, but yeah, so thanks to data analysis and computing, so we can kind of reproduce this stuff. Okay, and so let's go to ultra high energy gamma astronomy. Ultra high energy means so it's TV, and now we go to PV, pelotonia. Yeah? So now again we have to recall our old school technique by placing a surface detector, but now we do not place them in thousands of kilometers. We just place them in 1 square kilometer, but very dense. So we made 1,000 of detectors from just 1 square kilometer, and most sensitive and most, let's say, ultimate one is built in China. So it's like an artist's representation of this. So you can see again this grid structure, so we call it laser detector. So which is actually located at a very high altitude of, as far as I remember, about 4,000 to 5,000 meters. So it's in a kind of, yeah. So the atmospheric pressure is like maybe 70% of a nominal one, so maybe even less. And so here you can see already like a sky in PV detected by laser. So Hess was the TV, now PV, so it's like a 3 order of magnitude. So these energies are not completely accessible in Earth. And these guys are only our galaxy. Yeah? So we have also extragalactic, but for extragalactic sources, it's more hard to detect because, I mean, the distances are, again, orders of magnitude higher. So we have flux really low. And this actually very famous region is Cygnus 1. So you see this, yeah, Cygnus. It's very nice bird, and yeah, it's a very dense region and pretty, now it's like a most, I guess, interesting region after laser detection, because we don't know what is there. So there's like so-called Cygnus cocoon with a very complicated stuff and so on. Actually, it was nearby in our galaxy, and I mean, before, I guess, last year, so this result was presented last year, we had no idea, yeah, how this looks like. So it was completely, I would say, blind in such high energy. So actually, history just, yeah, creating on nowadays. Yeah. Okay, so now I come to my next part. We are approaching the main topic, yeah, big data. And so besides gamma quanta, we have a neutrino, yeah, and you know that neutrino is the lightest particle, so it's already proven that it has some mass, but we cannot detect this mass, yeah. It's like, okay, it's massive, but no idea how light it is. Yeah, and neutrino is a very weak interactive form. So here, some interesting numbers that, yeah, cross-section of MEV neutrino. So this neutrino is actually producing stars in supernova. So I mean, to fully absorb this neutrino, we need a water layer of 100 light years. So it's almost undetectable. Yeah, and so it was, since it was almost undetectable, it was detected only in 1956. Yeah, it was a radiogram from to Fermi, who actually predicted this neutrino. I mean, the existence of this particle and predicted its properties. Yeah, and already in 4 years, so Soviet academician Markov, Moisei Markov, already in some conference already said, okay, so we can just go into some natural lake of a cubic kilometer of water and fill this with detectors. And then we can detect neutrinos even from astrophysical regions. So it was in the golden age of science, like 1790s, when it was like really, yeah, science was really popular and prestigious field both in Soviet Union and USA. It was a collaboration between these two countries to build such a huge detector. I mean, this plan is still not really fulfilled by nowadays detectors. So it was a workshop in 1975 in Washington. So it's actually shows actually how science can make this, yeah, peacemaking and so on, yeah, cooperation during the Cold War. And this was actually proposed a volume of 1.26 cubic kilometers. Yeah, it's like kilometers times kilometers times kilometers. Yeah, with 1,200 strings. So you can see the strings. So it's very old plot from old book, and 20,000 optical models. So you remember, so has, I mean, Cherenkov telescopes has 1,000 of such models, and to detect neutrino in water, we need this size. So it's like about 10K each one. So you see how how science was like at that times. There was also a plan to be equipped with acoustic detector, more simple one, but with 2 orders of magnitude higher volume. Yeah, and so it was active collaboration until 1980. So then, due to political reasons, due to war in Afghanistan, so this relations was frozen very fastly. So yeah, and yeah, Americans still working this until 1995, but actually the experience acquired in this project was then actually divided in two different projects. So first called Amanda in the South Pole, which now turned into ice cube, and the NT200. So it's a telescope on the Baikal water. So it was very nice results from this telescope in the very beginning. Then due to economical reasons, it was like kind of suspended. And now they also start to in a few years they started to, let's say, to build also big volume telescope. Before I go to astrophysics, I just want to show you very beautiful picture also from neutrino detector. So it's a Kamiokande mines, or now it's Super Kamiokande in Japan. So they have a mines, and they just fill this with ultra pure water. So you can see these guys in a boat, and this is actually like a sphere covered with this photo electron multipliers with this size. So okay, I mean, Japanese can afford this because they actually monopolist in production of these photo multipliers. They can do this. And here you can see, so it's like 50K of super pure water and the 13K PMT. So it's like 13,000 of these detectors. So it's very small detectors, not for truly astrophysics, it's mostly for sun studies and so on. But actually, Kamiokande was the first detector discovered in neutrino oscillation, which actually proven the existence of the mass of neutrinos. So we don't know the mass, but we know that it's not zero. Yeah, it's funny fact. Yeah, and then we go to truly astrophysics. So I told you it was Amanda after this Dumont project, and so now, mostly Americans built Ice Cube Observatory. It's very crazy project. So they just go to South Pole and drill a holes with boiled water. So they just boiled water, benzene or gasoline, and then just melt the ice and put these photomultipliers forever. So they are not extractable anymore. And it's likely similar if you send satellite to the space, so you cannot repair. So you can see these strings, and these strings consist of the photomultipliers. This actually kind of properties of this, and this was already deployed in 2011, and so and in 2013 there was a very strong evidence of detection of the astrophysical neutrinos. So what this two plots shown? So this each ball, each sphere corresponds to a signal. The size of the sphere is the amplitude, and the color just shows the timing gradient. So you can see, so neutrino just passing like this way, and so not neutrino, sorry. So neutrino actually cannot produce light, but it produces a charged particle called muon. And then muon, so just traveling through the ice, produce Cherenkov light again, but in ice, and then just highlight these photomultipliers. And the distance between strings are 125 meters. So it's again like cosmic ray scales, but in ice. And in this case, we don't see such a track because in this case, neutrino just destroyed nuclei of a water, and then it produced kind of the same mechanism as air shower. So it just produces a cascade which kind of blows in the ice. So now I kind of try to shortly explain which particles we have. And so we can detect this, but we can detect this with the different setups and so on. But we need to connect them, because I mean our main point is actually to understand how this particle accelerates and what are the properties in these accelerators. And this actually studies made a new brand which is called multimessenger astronomy. So what this means? This means that we doing astronomy, but you remember that astronomy is like classically it's only like electromagnetic, it's only photons, but multi-messenger means that we try to do astronomy both with neutrinos, cosmic rays, and even gravitational waves. So this is just a simple example, how this astronomy can look in theory. We have for example, neutron star merger, which produces gold, and this gold somehow travels, and let's say, collides with Earth from opposite direction when this happened, and we say, okay, we don't know from what direction this gold actually arrived because it's deflected in magnetic field, but as well, it can produce neutrinos and can produce gamma rays, and you can see that gamma rays also can be absorbed, so it's also pretty hard, yeah, to detect gamma rays, and as well gravitation, and we know that we detected them. Yeah, and so here, why it's multi-messenger? Because, I mean, very roughly speaking, yeah, so if you would detect neutrinos, protons, and gamma rays, so they will have such a kind of funny connection, so it's in energy and so on, so they're spectrally they're very close to each other. So in principle, if we detect several particles from the same source, we can make a spectrum, multi-messenger, not in frequency, but already spectrum in different species of particles, and try to study what exactly happens there. I mean, neutron stars is a very complicated object because it includes special relativity, general relativity, quantum physics, I mean, all the top physics. So they work in extreme regime, which we cannot actually reproduce on Earth. Yeah, and this is actually a reaction how we can connect these particles and produce. Just to let you know that this particle chemistry is much more simple than normal chemistry. For now, thanks to development of quantum field theory. Yeah, and this like just a summary. Yeah, we already know that cosmic rays ultra easy to detect, but we never point back to source. Gamma rays, it's, okay, easy. Now cosmic ray ultra easy. Now gamma is kind of easy. So they point to source, but it has like a megaparsec horizon. So on the megaparsec, they suppressed very heavily because of the interaction with the background in the space. Yeah, so neutrinos are hard to detect, and they have no horizon. So in principle, we can see neutrino from whatever location in the universe, starting from the very, very cosmological distances. So in principle, if something happened like in gigaparsec scale, and we detect neutrino from it, yeah, it's fully possible, whatever energy it has. Yeah, and gravitational waves is ultra hard to detect. It's in principle point to specific source, also has no horizon, but it gives us hints on what is going on the very, very extremal cases. Okay, so I guess you heard about this very famous multi-messenger detection. I guess it's kind of most important one, multi-messenger detection, and the Fermi satellite, which detects gamma rays in a hard X-ray regime, detected coincidentally detected a signal from neutron star merger, which detected both by LIGO. So it was like a first proof of the, let's say, neutron star merger detection, because for now it was like kind of theories that this kind of signals detected not only Fermi but other optical telescopes are likely neutron stars. But when we detected gravitational waves, it was like fully proven, and then we can. Yeah, I didn't remember how many gold produced in this collision, but I guess it was like maybe thousands of tons of stones. If somebody likes to go there, you can try. Okay, but yeah, it was a very famous one, but the first one, actually including neutrino, was detected actually pretty almost, I guess, yeah, 35 years ago. It was a supernova explosion in a large Magellanic Cloud, so it's like 50 kiloparsecs. It's just a satellite of a Milky Way. Yeah, and now, so here we can see the shell of the supernova, and again, different wavelengths. So shell is very nicely visible in X-ray, because the particle acceleration happens on the shock, yeah, so we can produce a high energy on the shock. And as well, we detected a few neutrinos. So you can see it's like 20-something neutrinos detected on the experiments located at the time. So it was like a Kamiakanda. So you see this in a few slides ago. Baksan in the Caucasian Mountains, and EMB also in some mine in USA. And so here we can see how this looks like with neutrino. Yeah, but then when we have an ice cube, so we can detect also neutrinos, but with very high energy. So supernova explosion, okay, it's like funny, but what we can go on really extragalactic scale. So it was actually alert from IceCube, and so you can see in, already almost 5 years ago. Yeah, so it's actually kind of neutrino threats from IceCube. So it was very energetic one. That's why it was really kind of easy to distinguish the direction of it, and then IceCube sent alert. And yeah, so this alert again was detected by Fermilab, by satellite, and as well by MAGIC. So this telescope I mentioned, which located in Canarian Islands. Yeah, and this is actually how they look like in Fermi, how they look like in MAGIC. So actually, this red contour is uncertainty of detection from IceCube, because yeah, this in ice detectors, moreover, neutrino cannot really kind of be focused or tuned for the to have very nice spatial resolution. But yeah, it's fine, and it's already, it's not like a 5 sigma significance, yeah, because it's like only single neutrino. But yeah, estimating the background, it was like a 3 sigma. So it's nice evidence that this neutrino actually associated with these guys. And yeah, as I told, if we actually add neutrino here, yeah, so we can plot in every frequency plus neutrino, yeah. So it's like from energy, so from 10 to minus 6 to 10 to 15, yeah, 20 orders of magnitude. So it's a blazar, it was blazar, active galactic nuclei, and yeah, so it's, you can see that we can scan it in a different domains. Okay, and as well there was a kind of attempt of historical archival studies of the source. They just try to, I mean, they have a data of neutrinos, they try to, say, play with statistics a little bit, and they IceCube people detected also kind of burst from the source. There was a different explanation of this burst. So when radio people start to look into it, they found, let's say, like a two rotating black holes with two jets. These jets actually colliding with each other, which can likely produce this emission. So it's very complicated source, and we actually were not expected that it might be such complicated stuff. But it's, if it's true, I mean, if the statistics correct, and if this 3.5 sigma, I mean, it's not like a 5, but it's like, I mean, we put sigma threshold just arbitrarily, yeah. So if it's true, that is like a first astronomical source plotted in neutrino. So you can imagine, yeah, how in 50 years we actually developed from a single detection to already making kind of map. Yeah, so now I will go to, let's say, next generation Astrophysical experiments. So it's very biased selections where I want to focus on data rates on them to, let's say, to discuss them, yeah, big data stuff. Yeah, so first of all, I guess this is the most ambitious one, is a square kilometer array. So you can see this, like on the, in this poster on the very end, there's like kind of antennas. Yeah, and then like want to make an array. I mean, it's already started to be deployed. So it's just 1,000 of antennas on the square kilometer. So it's just a square kilometer just filled with these low frequency antennas. Yeah, and so you can see that the data transfer rate is 7.2 terabits. Yeah, it's like a just guess comparable to internet one, right? And so these guys will be located in Australia, and already in South Africa there's also a prototype with a high frequency telescope. So it's like a mirrors which reflect high energy, high frequency radio in this camera. And actually this camera consists of the many pixels, which are also kind of small antennas, yeah, for low frequency. And here you can see it's like 8.8 terabits. So actually this data rates and so on will exceed the rate in a Large Hadron Collider, and already comparable to what we have on the internet now. And yeah, you can just Google the size. They give some funny examples that with cascades you can detect radar in the nearby planets. Yeah, so it's super sensitive guy. So the other stuff I want to point on is like LSST, Legacy Survey of Space and Time. Oh, sorry. So it had, so it's almost deployed. It had like 3 billion pixels, so it's just the hugest camera in the world. I mean, not only in telescope, but I mean, in general. Yeah, and it has like 30 terabytes data per night, so it's a really like a big data rate. And this data is actually fully consist of the photos. So this telescope will do really photos of the sky, and yeah, we need somehow analyze this data pretty fast. And the entire sky, I mean, accessible sky in this area, so we'll make it several times per week. So it's a really like scan both in the space and time, snapshots of the sky. It's really cool. Yeah, sharing of telescope array. So you know how telescope array looks like, and you see that has 5 telescopes, and here it's like planned telescope array in La Palma, and this planned telescope in Chile. So we just try to scale like from 5 to 100 telescopes. And of course, generation 2 of IceTube. So I told you how they put the detectors in the ice, boiling the water. So this red one is like first, I mean, current state of IceCube, and they want to just increase in volume in order of magnitude, like 10 times. They already discussing how to do this. Some pieces already deployed and so on. And of course, gravitational wave detectors, but we don't have time to discuss this. But yeah. It's yet another lecture here to discuss this. And since we're saying about particle physics, gravitational waves are not, I mean, gravity is not detected so far, so formally it's like a particle physics, yeah. Okay, and let me go to my very last part of the talk. Hopefully you're still interested in this. So, yeah. So, okay, so why big data? So, because here in this plot you can see expected data volume in petabytes. So, I mean, this line is like a 10 petabytes, so this is like 100 petabytes per year. And yeah, so as I told you, so in SK you can see the data volume is really huge. And in principle, I mean, TTA also approaching so on. So, I mean, by like arbitrarily, yeah, if you have petabytes, it's like kind of be considered as big data. So yeah, so there are a lot of timelines. So some experiments already commissioned, some will be commissioned soon, and so on. But yeah, we will have this problem soon. Yeah, and there are already kind of different initiatives for the global analysis and data center in astroparticle physics. Yeah, it's like a very nice ideas how to make this, because I mean now we have this data is really kind of distributed around experiments, now nice protocol communication and so on. Of course, we need to education, big data science and so on. So in principle now particle physics is already kind of a mature field, and now we say facing a major problem. So both related to data handling and to education of next generation. And yeah, so the main idea is to follow the FAIR principle. So maybe it's findable, accessible, interoperable, and reusable. So that means that if we acquire some data, this data should be handled in order that the next generation of scientists can actually reanalyze this data. For example, if all of your scientists, I don't know, just disappeared, so this data should be reanalyzable. Yeah, so this is like a more detailed presentation. So what actually we want to do? So actually there are different proposals, in particular Germany, and we actually working with people who actually doing this stuff. Yeah, so as I told you, so it should be available and analyzable. Also, we need a lot of simulations because first let's say to at least start and build experiment, we have to simulate the data rates and so on, and whether it's actually feasible to do or not. And as well for developing data analysis, we also need to perform a lot of simulation. Sometimes these simulations are even more computational expensive than data analysis itself. Yeah, and of course real time, because we have very short transient. Yeah, it's very nice stuff, open access, education, and so on. Yeah, so this stuff is actually now in progress, and in frame of JetBrains research, we're actually working only with these guys. So we don't use any proprietary data, so we fully support this open data and so on. And yeah, moreover, there's like a very nice slogan. It's like a public data, I mean, public science for public money. Yeah, so as a scientist, I mean, we should fight against proprietary data. Yeah, and here I just want to show you some kind of science cases for pure data science, yeah, unrelated to astroparticle physics. So we have Zwicky transient facility. It's actually LSST pathfinder, so it's very field of view, and so it streams alerts for transients. For example, since it's very field of view experiment, it has a supernova each night. I mean, not galactic supernova, but I mean from entire sky. There's also some subthreshold event which cannot be reconstructed online, but can be somehow correlated maybe, and so on. And of course, this requires algorithm techniques for archival search as well as for transient classification. Now, many people, many groups actually work on this, either using some classical methods, investigating this light curves of the bright phenomena, or even machine learning and so on. And another class of events, so there are not only two classes of events, I just give you some couple of science cases to make an impression. It's a so-called data challenges. So as I told you, that SKA, LSST, and CTA, they had like a petabyte data scale, and we actually need to develop method to handle this data. And actually, for this experiment, there are so-called data challenges. So they just kind of produce a mock data. No, roughly speaking, just kind of upsample what we have, upsample maps, so produce maps with a very, very high resolution, and they just give this data in open access, I mean simulated data, not real data, and say, okay, yeah, try to analyze our data and try to, it's kind of maybe Kaggle competition, yeah, but Kaggle competition is kind of sport one, and this like for something which should be ready for production. Yeah, so I just will say a couple of words. I mean, our ideas on this JetBrains research is particle physics. So we just built this lab half a year ago. And yeah, the main important, I guess there's two main points, why we actually did this. The first is actually importance, although we moving into better by scale, but the importance of computing for astrophysical physics is really underestimated. So sometimes this activity just not funded. Yeah, like do whatever you want, but we will not pay for it. Yeah, and there's also like a kind of psychological, maybe social factors that there's kind of demand to be involved, because yeah, astrophysics is very exciting. Yeah? So when you say that you're doing astrophysics, that people say, oh wow, cool. Yeah. And yeah, and we use this opportunity given by JetBrains research mostly. So we just there are some education programs, workshops, and so on. And so students from computer center just come to us, apply to our project, and then apply their practical knowledge for fundamental research. Yeah, and so what we do, so we again doing sophisticated analysis of open data, so mostly machine learning, because most interesting field. Yeah, and as well for some visual observatories in the radio array. So I did not cover radio technique in this talk because it will be like really a long one, but just believe me, there is also very important one. And yeah, of course, outreach, for example, we try to make some common publication with data team. Yeah, and let me come to my conclusion. So I'm almost in time. Nice. So yeah, so now we are really mature field. We go into pelascale era, but unfortunately for now, so each facility has its own data handling protocol, and sometimes they're not optimized, or the communication between different facilities are also pretty complicated, or the API is not as ideal as it could be. Yeah. There are some global trends towards open data. There's, of course, some reaction on this. Some people do not like to share their data because they like to make them discovered by them all. But for example, NASA is actually pushes towards open data. So in principle, every NASA experiment has a very short embargo period for the data. So like Fermi, I guess, has like 1 day. So, but transients published immediately. Yeah, and there's also active developments towards global data and analysis centers, especially here in Germany. Yeah, and we just tried, and, I guess, successfully, yeah, make such attempts to cooperate between fundamental science and some private sector in frame of JetBrains research. And yeah, principle that's all from my side. I'll be happy to answer your questions or questions in chat. I don't know if there are some.
I'm curious, when you're showing different kind of rays and particles coming to Earth, and you said the charged particles, they don't have straight lines, they pass on that. I suppose they don't come at the same time as well. You
Yeah.
use them to.
Yes, indeed.
Can you use them still to
Uh,
complete a picture of some event? I don't know.
yeah, unfortunately, cosmic rays we have like only a kind of integrated flux, and so we know that we have such flux. I mean, integrated. Yeah. And by this, in principle, we can estimate how many, for example, supernova explosions we need to actually describe this. So we cannot correlate them timely, but we still can, make a population study. Yeah, yeah.
Which way the data is stored in the telescopes?
So there are different ways of, yeah. One of the main problem in astronomy, maybe not very important one, but it's they're allocated in some middle of nowhere. Yeah. So in past time, sometimes I mean for Hess, sometimes I guess data was recorded with streamers or to hard drive and then just physically transported. Now we have internet connection, but it's still like. And then in data centers is already kind of recorded in a more appropriate formats, like sometimes CERN root or HDF5 or whatever. Yeah.
Let's say, I didn't see the questions on the channel. How do you think and share the data that you have in data centers, or how do you copyright data?
Yeah, there's a problem that data oftenly proprietary and different telescopes just share some subset of data. So let's say, okay, we detected some transient, we give you this part related to transient and that part and so on in some any format. There are no like a really inter experiment or inter observatory data centers. There are some kind of transient servers when experiment just publish some very small subset, just summary that we detected such kind of event and so on. Yeah.
And we have some cooperation with CERN. They have very nice open source solution for such stuff like special buffer file systems.
Yeah. Some of the solution are really nice, some not really nice, and historically we should use them. But yeah, of course, we have cooperation. For example, we try to use their experience in grid computing. So I mean, they are really advanced in this. I wouldn't say that data formats and software ideal, and many experiments actually trying to go for let's say just an open source solution like from CERN format to HDF5 container, for example. But in terms of grid computing and file systems for grid, they pretty experienced it, and at least at the first step at the beginning, these initiatives, yeah, try to take their solution, or sometimes the institutes which participate in certain activities, they, for example, grant us some computing resources that we can test how it works. Yeah. I mean, I'm not sure how we'll give this SKA because I guess they will build their own infrastructure, just take into account all the bottlenecks with the LHC and so on. Okay, yeah, I guess.